না, এখন আসেনি না সোমা। সীমা, তুমি কি দেখাতে শুরু করবে? স্নেহা, তুমি দেখাবে পিপিটি?
হ্যাঁ, মানে ক্লাসের জন্য তো
হুম।
ফ্যাক্টর অ্যানালিসিস এর।
হুম।
হ্যাঁ, যদি মানে স্টার্ট করে দিতে পারি আমি।
হ্যাঁ, তুমি তবে স্টার্ট করে দাও।
হ্যাঁ, আমার শেয়ার করতে হোস্ট হতে হবে।
দাঁড়াও, আমি করে দিচ্ছি। হ্যাঁ, এবার তুমি শুরু করতে পারো।
আচ্ছা, আমার স্ক্রিন দেখা যাচ্ছে?
হ্যাঁ, দেখা যাচ্ছে।
ওকে, so we will be dealing with factor analysis today. So this is table of content. I am not going through it. I will be uh, explaining all these things within this class. So at first, why do we need factor analysis, right? This is the first question. So, suppose you are a psychologist and studying human personality, and you have 500 participants in a questionnaire with 50 questions. Okay, and you want to know about their behavior, emotions, and thoughts. Now you have 50 variables. Like if you consider all of the questions like one variable, then you have 50 variables. How do you make sense of all of this data? Like I have considered these 8 questions here for better understanding, and you know about these questions like, are you sociable, do you feel anxious, and this type of things. Now want to group them up. Like we can't deal with 50 variables at the same time, so we want to group them up. And we will be dealing with like 4 or 5 variables, and for each variables there will be sub variables, like these questions will be in some particular group. So for making those kind of group, what can be the problems and what will be the solution we will be getting with factor analysis? So first problem is multicollinearity, that out of those 50 variables, it might happen many variables measure the similar thing. So we will not be able to understand whether they are useful or not. So it can be a problem of multicollinearity. Overfitting, same thing. Like 50 plus predictors are there in a regression with 200 participants. Model does not generalize, right? Interpretation, hard to explain each of the variables separately with coefficients. Statistical power, that is more variables can make more noise, and harder to find true effects, and missing structure also. So by using factor analysis, we will be getting the solution. So what is the solution? That is, identify the latent factor. What is latent factor? That is, if you have 50 variables, and suppose there are 5 variables in a they can measure the similar thing. So they can measure a particular latent factor. Okay, so it can be like anxiousness, it can be anxiety and nervousness, this kind of things. Reduce the dimensions, that their overfitting can be there as a problem. The for factor analysis, the solution is a reduction of dimension, that is 50 variables into 5 meaningful factors. Improve interpretability, that we can't deal with 50 separate coefficients, right? So we'll be dealing with 5 exact coefficients which will be presenting the latent factors. Better models that use factor scores as predictors, that is cleaner, more powerful analysis, reveal structure, that it can help you to reveal the exact structure and the psychological traits. So what is factor analysis? This is the definition. Like factor analysis is a multivariate statistical technique that identifies a smaller number of unobserved, that is latent variables called factors. Those the I am talking about the latent variables, that is like anxiety and nervousness. This kind of things are called factors here, that explains the pattern of correlation among a larger set of observed variables. What is observed variables? The question you have, like in previous slides, you can say, sorry, these are the observed variables. You can get data from the respondents directly, right? But you can't say that yes, the you can't get the data of anxiety or nervousness directly. These are hidden, these are latent factors for us. Okay. So yes, so what is latent variable approach? Factors are unobserved constructs. We cannot measure anxiety directly. We infer it from behaviors and responses. Correlation based, that is FA, that is factor analysis, works as analyze by analyzing the correlation or covariance matrix. I will be dealing with this in further slides, that what is covariance matrix and how we can get help from it, of observed variables, not raw data directly. Data reduction, that 20 like we have 50 variables, we cannot deal with exact 50 of the coefficients, right? So we will be dealing with two or three or five factors that capture most of the variances. Construct variability, that is widely used in scale development, that is for scale development we will be dealing with that EFA, that is exploratory factor analysis. I will be discussing this in further slides. Widely used in scale development to verify the test items clustered into theoretically meaningful dimensions. So there are two main type of factor analysis, that is EFA and CFA. What is EFA? Exploratory factor analysis. The name itself suggests to explore, right? It is exploratory factor analysis. You can explore, discovers unknown structure. Okay. And confirmatory factor analysis, it, like the name also suggests, to confirm. Like we have the test of hypothesis, we have that hypothesis and we want to confirm, that is, if if that suppose GAD, a scale GAD, you all know about GAD, can it measure the anxiety level or not? We use their CFA, not EFA. Okay. We want to just confirm our hypothesis. So till now, any questions? Anyone?
No, ma'am, understood.
Okay. So this is historical background, and we don't need to study this history. So I am skipping this. You can just have a look when the material will be given. So these are terminologies. I have explained that is what is observed variable, and these are the definitions, proper definitions. And latent variable also has been explained. Now the factor loading. What is factor loading? The correlation or the regression weight between an observed variable and latent factor. The range is -1 to 1. A loading of 0.80 means 80% of standardized variance of that item is shared with the factor. Like if we have the observed variable, is it correlate to that latent factor or not? We will be knowing about this by this factor loading. Okay. I will be showing you the exact model, then it will be more clear for you to understand. High loadings indicate that item is good indicator of that factor. H square, that is communability. What is communality? What is communality? The proportion of variance in an observed variable that is explained by all factors together. What is that? The exact equation is the square of the factor loadings, nothing else. Sum of the square of the factor loadings, nothing else. Okay. The range can be, because if like all of this is positive terms, that is the range will be from 0 to 1. If there is a threshold of like 75, like 0 75%, if h square is 0.75. That means 75% of variance is explained and remaining 25% is unique or error. That is unexplained part. Like, you know that I have already told in previous classes that each model have two parts, explained part and unexplained part. If this is 75%, the variance can be explained if the h square is 0.75. So then the uniqueness or specific variance, the proportion of variance in an observed variable not explained by the common factors. That is, I have told this unique or error part, this is being explained in this form, like 1 minus the explained part, that is unexplained. Okay, I am not going through all of these ppts, I am just telling you the exact concepts. Factor score, what is factor score? That is, this is a weighted sum of each of the factors. Okay, weighted sum of each of the factors, what wi are the factor score coefficients. This w1 w2, for each of the factors we have some weight, and f is the sum of those weighted factors. Eigenvalue, it is a concept of linear algebra. So I am just going through this definition, and we will be dealing with in further slides. Associated with each factor represents the total variance across all observed variables explained by that factor. Eigenvalue, what is eigenvalue exactly? The sum of square of loadings. What are the loadings? This lambda values, sum of square of the loadings for that factor. The Kaiser rule will be explained again. Retain factors with eigenvalue greater than 1, that is explaining more variance than a single observed variable. Scale, which scale do we use? Like for p variables, we have p variables, I have mentioned it in factors code. Some of the eigenvalues will be p. For each of the eigenvalues it will be 1, and if it is greater than 1, then it will be like explaining more variance, and for ideal case we will be considering 1. So all sum of all the eigenvalues will be p. Factor rotation, a mathematical transformation, like we use it when we have non-normal data. So this is a transformation, like mathematical transformation applied for to the initial factor solution improve interpretability. Rotation does not change the total variance explained, it just redistributes it across factors. Two type of factor rotations are there: orthogonal rotations, example of this is varimax, and oblique rotation, example is promax. This second one is more realistic use of in psychology. So this is the form of model, like xi. What is xi? Xi, our observed variable. These are loadings, I have already told, factor loadings, this lambda I k, and fi, fk, that is f1 f2 up to fk, these are the latent factors. Okay, and the like for each of the cases the assumptions will be, for expectation of xi will be 0 and variance of xi will be 1, and for similar for the f also, expectation of fk is 0 and variance of fk is 1. And this is the error part I have explained, and similar case for this also, that is expectation of error part is 0, that is uncorrelated with FIs, that factors. So this is only the matrix form that I have explained in previous slide, in summation form. In this slide it is only the matrix form, nothing else, so I am not re-explaining this. So now this is the main point of our this analysis, that is the correlation matrix. So factor analysis works by decomposing the correlation matrix, that is R. Here you can see this matrix. For all of the diagonal cases it will be 1. Okay, and interpreting the matrix, how we can interpret, like nervousness, and nervousness you can see that all of the diagonal values are 1, right? Nervousness, anxious and worry correlate highly why can we say these all are highly correlated? Because each of the cases the value of r is greater than 70 sorry 0.70, right? So they likely load onto the same factor, that is anxiety or neuroticism. For social and social and outgoing correlate highly. Just a second, just a second. এটা class চলছে, class চলছে, okay. Social and out am I audible? Hello,
Yes, ma'am.
am I audible?
Yes,
Yes,
ma'am.
ma'am.
Okay, fine. So sociable and outgoing correlate highly, because why we can say, because r is equal to 0.74, as you can see here, this value. So they load onto a different factor, that is extroversion. But for the low correlations, right, this 0.08, like which are where the r values are 0 less than 0.15, the cross factor correlations are low. So two groups measure different constructs that fa will clearly separate them, right? So this point I have already explained. So in this matrix, does anyone have any question? Like, what can be the threshold? How we can interpret it? Like for these dark colors, these are highly correlated, right? Because these are greater than 50. So we can make one group of them. And for those who are greater than 02, they are correlated but not that much. So and for this, those are less than 0.15, these are actually very low correlation they have, so we can't group them up. So is it clear to everyone? Any questions? Anyone, any question?
তুমি এই কালার গুলোর মিনিংটা ভুলে দাও।
হ্যাঁ মানে like for this diagonals I have used this color because these are one already. Perfectly correlated, you can say. And these dark colors like this one, which are greater than 0.50, right? This one, this, they are highly correlated, right? And those which are less correlated, I didn't put any color, like sky only. Any questions so far? Like, please
No,
respond.
ma'am.
Okay, fine. Because many things have to be explained, that's why. So the concept of eigenvalue I have already discussed, but still I am just going through this. What is the pattern? Like the matrix, these are all mathematical understandings. Okay, like from being a statistical background, I think this should be explained, but I don't know whether these are useful for you or not. So I am just giving some overview of this. So these are what is eigenvalue, I have already told, used by lambda. So this correlation matrix can be explained in this form, where r is a symmetric positive definite matrix. Okay, so this is also positive definite, this matrix also should be positive definite. This matrix can like determine whether that sorry whether that r, what is the nature of r can be. Okay, so eigenvalue is lambda here. I'm just going through it quick. What is the mathematical definition? That is RV equal to, where V is the eigenvector. I will be explaining this in this portion. And lambda is the eigenvalue, and V is again the eigenvector. So for a p variable analysis, sum of all eigenvalues, that is p itself, because we are dealing with the like ideal value where each of the eigenvalues we are considering one, and we have p variables, so the total sum of the total of eigenvalues will be p. And these are ordered eigenvalues, like after getting the eigenvalues we will be ordering all of those things, and if each of the eigenvalues divided by p into 100, it will give us the percentage of variance for each of the factors. Okay, like here is an example. Like if the lambda 1 is 2.85, and we have five variables, that is the mean, that is the p value is 5, then 2.85 by 5 into 100. So factor 1 explains 57% of the variances. Okay, similarly for factor 2 also. So total explanation will be factor explanation by factor 1 explanation plus explanation by factor 2. The total will be 91.4%, that is the whole variance will be explained. And this is a definition of eigenvector: a vector or the set of p values that points in the direction of maximum variance in the data space. Okay, so what is the mathematical definition? This is similar, like you can see the equation is exactly similar. The difference is the lambda is eigenvalue and v is eigenvector. I have just written down, nothing else. So in factor analysis, eigenvectors represent factor loadings after scaling. That is lambda ij equal to vij into the root of eigenvalues. Okay, what are the properties of eigenvectors? Each of the eigenvector has length 1. That is, length means we can use like modulus sign to exactly represent the length. Okay, that is will be unilength. Okay, because the length is 1. Eigenvectors are perpendicular, that is orthogonal to each other to the initial extraction. They define the axis of the factor space. So what is the interpretation of this eigenvector? Which observed variables have high value on these vectors, that is, those items long load strongly on that factor. Okay, so what is the decomposition? Like we have the eigenvector, we have the eigenvalues, what is the use of it? So first we start with the correlation matrix, that is R. Here you can see, solve the characteristic equation, that is determinant of the R minus lambda is identity matrix here. Like you have to solve the determinant here, that is equal to 0. You will be getting p eigenvalues that I have mentioned here. For each of the eigen value, that is lambda I, you have to solve vi, that is to get the eigenvector. For each of the eigenvalue we will be getting a eigenvector. Okay, select k eigenvalues to return, because for previous thing we have k factors. Okay, I have written it down. K factors are there, so we will be dealing with k eigenvalues. And how we will be dealing with the eigenvalues? We will use the Kaiser rule or scree plot, parallel analysis. I will be explaining those also. Then we have to compute the factor loadings. If you use some software like R or Jamovi, Farah ma'am will be explaining all those things through using Jamovi. So these are some, like you have to use some code, nothing else. You don't have to bother about this background study. I am just explaining this to, like, you have the clear understanding of what's going on behind the scene. So what is the Kaiser rule? If the eigenvalue is greater than 1, okay, so what does it mean? Like if an eigenvalue of 1 means the factor explains as much as variance as one original variable. Okay, if it is greater than 1, then it explains more the variances. Okay, it is simple, like we don't need to read all this advantage or disadvantage. I am just going through the exact pattern, what are the key concepts. Then the scree plot, it is a visualization. Like I will be showing this part and explain this part. Like if you put those eigen values, and you will be looking at the elbow step. Okay, before the elbow we will be considering only those factors, those are useful for us. And after the elbow, the like eigenvectors, sorry, eigenvalues will be less than 1. So we will not bother about those things. Parallel analysis, this is the like golden standard, I would say, to analyze this thing. So to compare the eigenvalues with eigenvalues from the random data of the same size, same sample size actually, return factors where actual eigenvalue is greater than the 95 percentile of random eigenvalues of that factor number. I will be explaining all those things using graph in last 2 or 3 slides and just giving the overview at present. Okay, interpretability. What is the theory of this? Written factors that make substantive sense of the context of your research. Like, what is the question of it? Can I give the this factor a meaningful psychological name? Like, if you have a factor, you you can think that these variables can be under this one factor, but can it make a group? It is a question here. Okay, can we give a psychological name to it? Do the items loading on it make theoretical sense or not? Right. So I have given an example that items about worry, fear, anxiety, all loadings on one factor. It is called neurotism. Right. So what is the best way to do this? First, we need to do parallel analysis. I have already told it is the gold standard examination, I would say. After that, to check whether we are right or not, we will be using the Kaiser rule. Then the script plot, it is a visualization purpose only. Then verify the interpretability. That's all. So up to this, how can we select the factors? Is this clear to everyone? What are the main rules?
Yes, ma'am.
Okay. So now the factor extraction. Like, we have made the factors, then how to extract the factors? Like, we have the mathematical approaches for this. Okay. So first, deal with principal axis factoring, that is PAF. Most commonly used in EFA. I have explained the EFA part again. Sorry, I have explained this part EFA, why we need to use, like, explore new things, explore the structure, right? So this is the mathematical structure. Replace the diagonal, like wait, this is R, where each of the diagonal elements were 1, right? You can see each of the diagonal elements were 1. For this case, we will be dealing with the communality estimates, that is h square. What is h square? The sum of the eigenvector, sum of the eigenvalues. What is the eigenvalues? The factor loadings, sum of the squares of the factor loadings. Then it would be r star. Okay, it is not remain like r only, it is the r star, that is r minus the error part. The extracts factor from the reduced correlation matrix. We will be starting with the hi square, that is the communality of ith variable, I would say, and the r square I, that is squared multiple correlation. It iterates until the communality estimates converges. Okay, these all of this thing will be doing in software. This is a background study only. Don't like be so much confused with this, because it's not your work to do. Okay. Then the maximum likelihood estimation we will be dealing with. Like, what is the main goal of it? Finds the factor loadings that maximizes the probability or likelihood of observing the obtained correlation matrix, assuming the multivariate normal distribution. Like, we are back of the mind, we have the assumption of multivariate normal distribution, but for each of the cases we will not be that much lucky to get that normality. Okay, so when we don't have that privilege, then we will be using principal component analysis. It is not truly factor analysis, but often confused with it. Like, these are the confusion among the students. So I will be just explaining this thing so that you guys don't get confused with the facts. Extract the components from the full correlation matrix, that is what is the full correlation matrix? That is the initial r, this one, not that r star, this one only, where the diagonals are 1. Components amount of all variances, that is common plus unique, that is this is the common only. Okay, and this is the unique. What is the unique? Actually, it is the error part. No measurement error model. Key difference: FA, that is factor analysis, assumed observed variables are imperfect measures of latent construct, but PCA treats all variances are meaningful. So, where to use this PCA? Data reduction only, no latent variable theory must be there. Okay, we can use it for only data reduction. No latent variable will be like we can't separate those thing and put in some latent variable. Okay, latent factor we can't deal with. Then the GLS, that is generalized least square method. The exact formula is Ri minus Ri hat. Where what is Ri hat here? Reduced correlations from factor model. Where to use? When data is not normal. For normality, we will be using MLE, that is maximum likelihood. When data is not normal, when we need to get to the generalized method, that is GLS, generalized least square. So this is the difference between PCA and FA. I have explained it. You can just go through this once, like what I have explained in previous slide, just written in a table form so that you can understand better. So I am not rereading all those things. Let's go to the next slide. So these are the factor rotations. What is the concept of rotation? Why do we rotate? The initial unrotated factor solution is mathematically correct but often hard to interpret, right? Each of the variable loads on many factors. Rotation redistributes the variances so that each of the variable loads high on each on one factor and low to other factor. This is the main structure. Like if you have, for each of the cases it can happen, like for one question that is xi, it can get like factor load to different factors for greater than 0.05. Then it is problematic for us, like for which factor should we consider that only, right? So by rotation we will be confirming it is a confirmation that the exact question will give a high load to particular one factor, so that we can choose that question for that particular factor. Okay, there are two rotations I have mentioned, that is orthogonal rotation and oblique rotation. These are the like types of this rotation. You can have a look for all those things. I am not explaining this. Like what are the simple structure of this? Like what is our aim to do all those things? Rotation, why are we doing the rotation? I have explained it, but these are the criterions when we should do this rotation. So you can have a look of this also. Like the basic concept I have already mentioned, so I am not re-explaining. So what is the difference between EFA and CFA? That is, I have told that EFA is you have to explore, okay, and CFA you have to confirm. So, what is the purpose of EFA? Discover the factor structure when no prior theory exists, that let data speak. Explore, just explore. And for confirmation, that is confirmatory factor analysis, test a pre-specified factor structure, theory or prior research. Like we have a prior hypothesis and we are just testing it. What is the constraint for it? Sorry. Sorry. What is the no prior constraint or loadings must be there. Every variable can load on every factor. Okay. For CFA, you specify exactly which item load on which factors. Other loadings fixed or fixed to zero. Okay. Research stage. When should we use it? Like in the early stage of research, like we have only the questionnaire and we have to get the idea why we are using these things, and we have the hypothesis. I have explained it, so it is good enough to skip. What are the output? For EFA, factor loadings, commonalities, plots, rotated factor matrix. And for output for CFA, this will I will be explaining all of these terms, that is what is CFI, RMSEA, SRMR, chi-square. I will be explaining all those model fit indices. Okay. And the software you can use like R. I usually use R for both of the cases, and examples are there, real life examples. You can just look into this. Next, going to the assumptions of factor analysis. Adequate sample size. For our thumb rule is to get a perfect analysis, like when we have the data that is n is greater than equal to 200. If it is less than 200, then the factor analysis will give us poor result. Okay, so our goal must be to get the n greater than equal to 200. And factorability of correlations, that is variable must correlate with each and other, otherwise there is no common factors to extract, right? This will be explaining for the specificity test in further slides. And data must be continuous. You can say that this Likert scale, all those things, you have this you have idea for all of these things. Absence of outliers, like we can't deal with the outliers, right? So to check whether it have outliers or not, we will be testing the like uniform normality test and QQ plots also. I will be explaining this part also. Just a second. Next, the linear relationship. That is, FA assumes linear relationships between observed variables and latent factors. Non-real relationships are not being captured. Right. For factor analysis, also we will be dealing with the linear relationship. Non-linear relationship, we can't deal with this. So how to check? We will be checking with the scatter plot only, nothing else. Okay. So multicollinearity, I have explained this part in first slide only. If we have multicollinearity, then we can't deal with it, right? So to deal with those problem, we need factor analysis. So multicollinearity should not be there. So these are the steps. Like, yes, the scenario I have already told. So these are the steps, what to do in this case. These are the questions for our questionnaire. Okay.
হ্যালো স্নেহা,
So
তোমার এখানে
yes.
এটাকে একটু ব্ল্যাক করে দিলে ভালো করতে, বা অন্য কোনো কালার দেখা যাচ্ছে না, মানে হোয়াইটের
আচ্ছা
উপরে হোয়াইট পড়ে গেছে,
আচ্ছা
হোয়াইট
আমি
ব্যাকগ্রাউন্ডের উপরে হোয়াইট টেক্সট হয়ে গেছে।
ওকে ওকে, আমি স্টাডি মেটেরিয়ালটা শেয়ার করার আগে এটা ব্ল্যাক করে দেবো, ঠিক আছে?
হ্যাঁ,
ওকে। So this is our correlation matrix. I have explained it already. So yes, for the previous cases, I have taken an taken an example here. Like we have 9 questions, and each of the cases will be dealing with yes. This is the matrix for us. Okay, as you can see, the diagonal elements are 1, and for these cases, like this, for the orange cases, what we can see, this can be under same factor, right? Because they are highly correlated. So this can be under same factor. For question 4 to 6, these are moderate. Also, these are very good. Like also these are greater than 0.50. Okay. So these can be also of same factor. And this each of the 9, you can see the square. This can be under same factors. Cross blocks, that is these blocks which are in sky blue or white, you can see the factors are distinct. And KMO, that is KMO will be explained in next slide, that is 0.84. and the test of p, that is 0.001. So we can proceed with this. Okay, so scree plot will be showing here like this. For these three, we can see that the eigenvalues are greater than 1. After that, we will be seeing some elbow, right? This portion, this. Okay, a sudden change here, sudden decrement. So this will not be under our consideration. We'll consider these things only. So you can see the variance explained, right? For these all of these cases, these are less than 5. So we shouldn't consider all of these things. So our decision is to extract only first three factors, nothing else. So again, this like for rotation, this is an example why we need to use a rotation. Okay, like for this case, you can see this question will give the loading in factor 1 0.84. Okay, so it has the highest factor loading. So we will be consider that this question can be under factor 1, this also and this also. For next three questions, you can see this can't be under factor 1 because these are too small, right? But in this case, for factor 2, these are greater than equal to greater than 0.5. So these questions can be under factor 2. Similar for the last three questions, this can be under factor 3. Any questions so far? Like, are you able to understand how can we extract the factors, how these loadings are working? Any question?
No question, ma'am.
Okay, just a second. So these are just the interpretation I have already told in the previous slide. I have explained this part. So these are just written in words so that you can understand while reading the study material. So I am not explaining this. So these are the factor scores, like computing participant score on latent factors. There are three methods. Method one, this regression method, Bartlett method, and Rubin method. Okay, these are mathematical perspectives and you don't need to bother about this because these are work of our software. So just go through this. And yes, the concept is when to use is most widely we will be using the regression model, okay, which minimizes the MSE of the prediction. And what is the use of this model? We will be using weighted least square here. Like for regression model, we won't use any weighted least square. It is a generalized form, that is weighted least square should be used here. And this where this can be used when multicollinearity is our concern. These are the three difference like different situations when we need to use this. Okay, like usually we use this regression when we have to deal with the weighted least square. The second method is appropriate for us when we need to use the when we need to deal with multicollinearity. The third model is appropriate for us, third method. So these are higher order factor analysis, bifactor model, and measurement invariance. So what is the concept? I am just going through the concept a bit faster because we have many things to be covered. So, what is higher order factor analysis? When first order factors correlate with each other, that is oblique rotation, we can factor analyze the factor intercorrelation matrix to find the higher order factors. Where to use it? Intelligence research, like first order factors, that is verbal, spatial, memory, processing speed. These are the phenomena when we need to use higher order factor analysis. Okay, then bifactor, when we have a general factor that is common to all items, and a group factor that is for specific domain. That is like for example, like we have depression scale, like yes, we have something depression scale. Then the general factor is all over psychological distress. The group factors are anxiety symptoms, somatic symptoms, and mood symptoms. Okay, like this is the main factors, and this is we can say that the sub
স্নেহা,
factor.
হ্যালো হ্যালো স্নেহা,
হ্যাঁ স্যার।
আমরা তুমি যে গ্রুপ ফ্যাক্টর বলছো না, ওটাকে আমরা বলি স্পেসিফিক ফ্যাক্টর।
ওকে ওকে ওকে,
ওকে।
ঠিক আছে। হ্যাঁ, so then the multi-group CFA, that is testing whether a factor structure is the same across the group, that is female male. Like we can do some cross culture analysis. Okay, like we can do some different countries we can consider, different gender we can consider, different races we can consider. Okay, so for this we use the level of invariances, that is configural invariance, that same pattern of loadings in all the groups. Metric invariances, that is loadings are equal across the group. Like we are imposing some constraint for each of the scales, right? Configural, metric, scalar. When the scalar need to be used, loadings and intercepts are equal, can compare the latent factors. Then the strict, this is the most like I would say hard to achieve. Like residuals also equal, like the E part, that is the EI part, should be equal, rarely met. This part is rarely met, like hard to achieve this. Okay, so go to the next slide. So these are the real life implications, the real life applications we have. These are the examples, some study of psychology, psychological science, some studies, so you can just go through it. So this is the pattern. Like if you have the results in R or SPSS or Jamovi, wherever, which software you can use, how to report. Like you have lots of indices, like lots of things will be shown in the R window, and each of them not to be used to write the result. So this is the writing pattern I have mentioned here, you can go through it also. So these are the mistakes, the pitfalls, the mistakes everyone does, and I have explained the whole concept, so I don't think that you guys will do this type of mistakes. You can just go through it, and nothing that much specific to be explained. Okay, so I'm skipping this part. So yes, these are the main thing for CFA. Like for this is to be explained, like chi-square. When do we use chi-square? Test whether the model implied, that is sigma, is equal to the observed sigma. Right, model implied sigma is equal to the observed sigma. Ideal case, what is that is not significant, p value is greater than 0.05. But what is the problem with large n? Always it will show the significant model. Like we won't we can't deal with the chi-square when we have large number of sample, that is n is so large. So we will be going to the next indices, that is CFI. CFI compares the fit of your model with a null model, which is like independence of we don't have any type of constraint here. That is like zero model or null model we have. The range is 0 to 1. Higher, if the CFI is higher, then we can say it has a better fit. The threshold is 0.95. If it is greater than 0.95, then it is excellent fit. If it is greater than 0.90, then it is acceptable. If it is less than 0.90, then it would be considered as poor fit, and we will not going to use that fit only. Okay, so next, that is RMSEA. Another constraint will be there, that is measure how well the model fits per degree of freedom. Okay, that parsimony adjusted. The range will be 0 to infinity. Lower the range here, for CFI it is higher the range, better the fit. But for RMSEA, it is lower the range and better the fit. If it is 0.05 less than 0.05, then it is like excellent fit, we will be dealing with this fit only. If it is greater than 0.05 but less than 0.08, then it is acceptable. But if it is greater than 0.1, then we won't consider it. Then SRMR, that is average discrepancy between the observed model and model implied correlation. The range is 0 to 1. If it is lower, then it would be better to be fitted. Okay. Same threshold as RMSEA. SRMR and RMSEA have the same threshold, so I am not explaining this. AIC or BIC, that is information criteria. Okay. Used model comparison, that is not absolute fit. Lower the AIC or BIC, better the fitting relative to the alternatives. Like we have alternative fits. If we want to compare with those fit, if it like we have fit 1 and fit 2, okay, we want to compare if one is better or two is better, then we will be using the AIC. If it is lower, for one model 1, if the AIC is lower, then it is better than the model 2. Okay. When to use, compare CFA model with EFA model, or bifactor versus correlated factor model. That's it. TLI or that NNFI, these are similar things actually, like CFI, but penalties, like sorry, it gives a penalty. Okay, if you are making the model so much complex, then it will show some penalty. Okay. The range is 0 to 1. If the value is greater than 1, possible the fit is excellent. If it is less than 0.90, then it would be considered as poor fit. So these are concepts, important concept for CFA. Okay. Next, these are the like whatever I have discussed till now. These are the like summarization slide. I have summarized all those things here. If you have any question, I am giving 2 minutes. If you have any question, please ask. All of the points has been covered in detail. If you have any question, please ask. Otherwise, I will proceed to next slides.
আচ্ছা স্নেহা, আমরা যেটা করি সেটা হচ্ছে, ধরো কোনো একটা ভেরিয়েবলের আন্ডারে তোমার যে ফ্যাক্টর লোডিং বেরোলো, ধরো
হুম,
তিনটে আমার ফ্যাক্টর বেরোলো, ওকে, ফ্যাক্টর
হুম,
লোডিং
হুম, হুম,
আইগেন ভ্যালু ফলো করে। এবার দেখা গেল
হুম,
যে আমাদের যে ফার্স্ট ফ্যাক্টর, যেখানে তোমার সবচেয়ে বেশি আইগেন ভ্যালুটা আছে,
হুম,
সেটার ক্যাপাসিটি আছে এক্সপ্লেন করবার।
হুম,
তার মানে আমি যদি আইটেম রিডাকশন করতে চাই কোনো
হুম।
একটা জায়গাতে, আমি তো শুধু ফার্স্ট ফ্যাক্টর গুলোকে নিলেই আমি পারবো। তার মানে আমার সেকেন্ড অ্যান্ড থার্ডটা আমার খুব একটা বেশি দরকার নেই, আমি তো সেটাও করতে পারি নাকি?
পার্টিকুলার ওই
নাকি আমাকে
অবজেক্টের জন্য, পার্টিকুলার ওই
হ্যাঁ,
অবজেক্টের জন্য আমি ফ্যাক্টর 1টাকে কনসিডার করব, সেকেন্ড এন্ড থার্ড আর রিডান্ডেন্ট ফর আস।
কারেক্ট। এবারে আরেকটা প্রশ্ন, এটা
হ্যাঁ।
আমি ইউজ করেছি, এটা খুব ভালো বলেছো ডাইমেনশন রিডাকশনের ক্ষেত্রে। আহ, আরেকটা প্রশ্ন সেটা হচ্ছে যে, অনেক সময় যেটা বলা হয় 0.3-র ওপরে হয়ে গেলে
হুম,
তুমি তখন সেটাকে কনসিডার করবে।
হুম,
যখন ফ্যাক্টর লোডিংটা তোমার পয়েন্ট
হুম,
থ্রির ওপরে হয়ে যাবে, তখন তুমি সেটাকে কনসিডার করবে। এবার আমি
হুম।
দেখলাম যে 0.3-র ওপরে হয়তো ফার্স্ট ফ্যাক্টরের কিছু ভেরিয়েবল ঢুকেছে, কিন্তু
হ্যাঁ।
সেকেন্ড ফ্যাক্টরে সেটা আরো বেশি হয়েছে। সেকেন্ড
আচ্ছা। হ্যাঁ।
ফ্যাক্টরে কিন্তু 0.3 হয়নি, মানে 0.3 সেকেন্ড ফ্যাক্টরে কিন্তু আরো বেশি দেখাচ্ছে। তখন তো
হ্যাঁ।
আমি ওই ভেরিয়েবলটাকে যদি নিতে চাই, তবে আমাকে
হুম।
তো সেকেন্ড ফ্যাক্টরটা নিতে হবে। মানে
হ্যাঁ,
যদি আমি
সেটা।
মনে করি আমার ওই ভেরিয়েবলটা দরকার আমার কাজে, তবে তো আমাকে সেকেন্ড ফ্যাক্টরটাও নিতে হবে, তাই না?
হ্যাঁ, লাইক আমি 0.3 এর থ্রেশহোল্ডটা আমি খুব একটা কনফার্ম নই, বাট আমরা ইউজুয়ালি যেটা করি, লাইক 0.5 এর থ্রেশহোল্ডটা আমরা বেশি কনসিডার করি, তাহলে ওটা আরেকটু রেস্ট্রিক্ট হয়ে যায়।
কারেক্ট।
সেক্ষেত্রে আরেকটু মানে আমাদের ফ্যাক্টরটাকে চুজ করা সুবিধা হয়। 0.5 এর থ্রেশহোল্ডটা যদি আমরা ইউজ করি। সো
আচ্ছা, আরেকটা লাস্ট যেটা, সেটা
হ্যাঁ
হচ্ছে যে, যে ধরো আমি ফ্যাক্টর লোডিং এর ক্ষেত্রে ফার্স্ট ফ্যাক্টরের মধ্যে আমার পাঁচটার মধ্যে ধরে নাও তিনটে আমি সিলেক্ট করলাম, ওকে,
হ্যাঁ
ধরো যে
হুম
কোনো
হুম
কারণ, বা সরি 10টা তোমার ভেরিয়েবলস আছে, তার মধ্যে আমার প্রথম পাঁচটা আমি সিলেক্ট করে নিলাম, কারণ ওদের
হ্যাঁ
ফ্যাক্টর লোডিং সবচেয়ে বেশি।
হুম হুম
এবারে যাদের এই ফ্যাক্টর লোডিংটা বেশি, তাদের
হুম
ওই যে ফ্যাক্টর লোডিং মাল্টিপ্লাইড বাই দেয়ার অরিজিনাল অবজারভেশন,
হুম
সেইটা দিয়ে তো আমি বলতে পারি ফ্যাক্টর স্কোর।
হ্যাঁ ফ্যাক্টর স্কোর ওয়েটেড একটা সাম বেরোবে, সেখান দিয়ে আমি ফ্যাক্টর স্কোরটা বলতে পারবো।
ফ্যাক্টর স্কোরটা তখনই বলতে পারবো, তাই তো?
ইয়েস
আর
ইয়েস
তারপরে যেটা আমি করতে পারি সেটা হচ্ছে যে, ক্রনব্যাক্স আলফা যখন আমি করব, তখন
হুম
আমার যে ওই প্রথম পাঁচটা ফ্যাক্টর যেটা বেরোলো, মানে
হুম
যাদেরকে আমি সিলেক্ট করলাম, ওই
হুম
পাঁচটা ফ্যাক্টরের যে অবজার্ভড ভেরিয়েবল, যেটা অবজার্ভ যে স্কোরটা আছে, তার
হুম
আমি তো ক্রনব্যাক্স আলফা করতে পারি, কারণ তারা তো আহ, তাদের তো নিজস্ব ইন্টারনাল কনসিস্টেন্সি খুব হাই।
হ্যাঁ কনসিস্টেন্সি আছে বলেই আমরা ওদেরকে সিলেক্ট করে নিয়েছি অলরেডি, রাইট? দ্যাটস ওয়াই
হুম।
আমরা কনভেক্স আলফাটা ইউজ করতে পারি এখানে।
হ্যাঁ, যখন আমরা আলফাটা করব তখন কিন্তু তাদের অবজার্ভ যে স্কোরটা আছে তার উপর বেস
হ্যাঁ
করে।
তার উপর বেস করে, হ্যাঁ।
হুম, ঠিক আছে, থ্যাংক ইউ। হ্যাঁ,
ওকে,
এবার এবার
সো
তোমার দেখাবে সেটা
স্টুডেন্টস
বলো। হ্যাঁ।
স্টুডেন্টস এনি কোয়েশ্চেন সো ফার?
No, ma'am.
Okay, okay. So these are the references. Like I have made these slides with using these references. You can go through this. So now come to the assumption checking. This is our last goal to achieve. Assumption checking. Okay. For normality, we'll be using the Sapphiro will test. In Stata or SPSS, these are just two-liner codes, nothing else. But in real life, this has a huge implication. So I am just going through this definition and the equation only. Okay. So what is why normality is needed? When we are using MLE, that is, I have already mentioned the ML part, that is maximum likelihood, right? So the normality assumption is needed for that. Maximum likelihood extracts assumes approximately multivariate normal data. Violation inflates chi-square statistics, distorts community estimates, and produces bias factor loadings. PAF is more robust, but normality should still be checked. So, what is the statistics for this? W, that is the statistics, that is AI into XI. These are ordered statistics. Okay, like these are in some uh, specific order. Like if it is x1, then it is the smallest. If it is xn, it is the highest. Okay, divided by summation xi minus x bar, that is the mean whole square. Okay, so I have explained this. These are AI are the coefficients, that is theoretically derived weights. Basically these are the weights. Coefficients are basically the weights. Okay, theoretically derived weights based on the expected values, variances and covariances of order statistics from a standard normal distribution. So these are the new this is the numerator. You can see that weighted sum of squares of these order statistics, and this is the denominator. This is the formula. You, like, in your whole life you won't use it anywhere. Okay, so just for theoretical background I have given this. So what is the implication, or how can we interpret it? The significance level is like 95% significance we have. We said alpha equal to 0.05. It means that we are willing to accept a 5% chance of incorrectly rejecting the null hypothesis, that is false positive. The This gives us 95% confidence in our decision. So what is our h naught? That data are normally distributed, and h1, that is the alternative hypothesis, is not normally distributed. These are the threshold. Like if p value is greater than 0.05, then 95% confident that the data is normal. If it is less than 0.05, we will be rejecting the null hypothesis, then the data is not normal. This is the table when to use which type of factor analysis. Like if the value of sorry, if the value of w is greater than 0.97 and the p value is 0 greater than 0.05, then it is normal. We can use the uh, maximum likelihood and pf also. ঠিক আছে, like both of these are usable for us. If the value of w is from 0.94 to 0.96, even if the p is greater than equal to 0.05, the data is normal, but we can proceed with fa. If the value of p is less than 0.05, then it is not normal. We have to go for paf. We can't use ml here. Okay. If similar, like if the w is less than 0.90 and the p value is less than 0.05, then it is not normal again. We have to transform it, and the transformation part will be explained next slide. And then we need to use pf. We can't use directly pf here. We have to transform the data first. Okay. So these are the same things. Like the I have explained this table. These are the same things. Okay. So I'm not explaining this. I'm just explaining this part. What are the transformations? Like to switch to PF when we need to PF, right? Principal axis factor analysis doesn't require multivariate normality used. Instead, we use ml. Okay, when we have normal data we can use ml, like maximum likelihood. But when we don't have the normality assumption, we need to use pf. This is a direct format. But sometimes for like previous case, for this case, when the w is less than 0.9, then we need to transform the data. So we can do log transformation for positive skewness or square root transformation to make the count. Then these are some methods that bootstrap factor analysis and how to report the data. Okay. And next, that is KMO. What is this? KMO is a statistic that used in factor analysis to assess the sample adequacy. Like I have already told that for FA, doing performing FA, we need the value of n is greater than equal to 200, right? So how to assess it? The exact theoretical details will be given by KMO. Okay. So indicating whether the data is suitable for our for identifying underlying factors or not. Like if we have less number of data, then the result will be misinterpreting. So it can happen that these factors are not that much reliable for us, but it can happen the data shows no, these factors are reliable. So it can happen. So we need to use KMO first to know the sampling adequacy. Okay. This is a test. This test for the proportion of variance among the variables that might be caused underlying factors. That is, KMO range is 0 to 1. If it is greater than 0.60, then we will accept those factors and we will be going for factor analysis. Okay. These are the variances. Like what are the proportion of variances? This what is the meaning of this? This is a shared variance and this is a unique variance. Okay. When the shared variance is greater than equal to unique variance, then it has high KMO and we can have a good factor structure. Okay, we will be going with the factor analysis when we have the shared variance is much greater than the unique variance. So these are the thresholds. When you will get the study material, you will see this. Like for acceptance, we the KMO must be greater than 0.07. Okay. Before that, these are not that much acceptable. So this is the statistics for KMO. You can see. Like what is Rij are the simple correlations. Like I have shown the correlation matrix before, right? These are only those correlations, nothing else. And Pi are the partial correlations. These are the exact correlations and these are the partial correlations. Okay. And again, you will not be using this mathematical stuff in your life. Just for mathematical background I have given this. And this is the scale, right? This, if KMO is in between the range in between 0.9 sorry 1 to 0.89, then we can say it is very very good for factor analysis. If it is below like 0.7 0.7 to 0.6 zero point 0.6, then it is acceptable but not that much good. If it is less than zero point 0.6, then it is unacceptable for us, we won't go for factor analysis. So these are the output for SPSS, because I have done this study, this kind of study in SPSS before. But Farah ma'am will be discussing all those things in Jamovi, so this SPSS result will not be not needed for you. You can have a look, but it's not needed. Okay. So this is parasitic test. This is the again the test statistics, where H naught is R equal to I. That all other correlation, what is I is the identity matrix, right? All other correlations is zero. Only we have the diagonal matrix, that is the one correlation. Those factors which have the one correlation, only those factors we have. Okay. If H naught is true, all the variables are uncorrelated, and we can't say that this factor this question 1, question 2, or question 3 can be piled up, can be grouped up in factor 1 or factor 2. This we can't say, because all of those are uncorrelated. Okay. So factor analysis cannot be proceed. So it is, we need a significant result to see whether those factors can be grouped or not. Okay, this is the main logic behind this. So yes, these are the steps. Like we don't need to do all those steps. Just some codes are there in Jamovi, you can perform this. Additional check for outliers, like I have told that if we have the outliers in data, we can't deal with those, right? We can't deal with that data. So to erase those outliers, these are the patterns. This is the statistics for us. Xi are the participant in is score vector, and this is the mean, that is x bar. And Si inverse is the inverse of covariance matrix. Okay, we can detect the outliers and just remove it. So these are the linearity check. Like from scatter plot we can do the linearity check. These are known to all of you guys, right? So I'm not explaining this. Like how can you do linearity check just for the graphs? We can see whether it is linear or not just to see the scatter plot, right? So again, the sample adequacy I have already told. If it is greater than equal to 200, then it is good for us. If it is not, then we need to check KMO, and if it is acceptable, then we can go for it. If it is not, then we can't go for factor analysis. Then for multicollinearity and normality check, we can use QQ plot. And the multicollinearity check, like if R is greater than absence of perfect multicollinearity. So how to detect? First we need to inspect if the correlation in the correlation matrix, if it is R is greater than 0.08 or greater than 0.0 greater than 9, then the pairs can be removable. We can suspect that there can be multicollinearity. So we need to remove those, otherwise we will get a totally wrong result. This is one thing, like use the correlation matrix. Other can be VIF, variance inflation factor. If it is greater than 10, then it has severe multicollinearity and we can't go with those variables. So next, the graph visualization. This eigenvalue concept, sum of role orderings, I have already told you. And I will show you the scree plot. This I have already told about the scree plot. This you can see the elbow here, right? These are higher eigenvalues these have, that is greater than 1. After this, a sudden decrement is there, elbow pattern, right? So just without testing anything, just to see the scree plot, we can say which factors to be included and which are not to be. Okay, so
আচ্ছা
this.
স্নেহা,
Yes, sir.
স্নেহা ওই এই তোমার এই এলবো প্যাটার্নটা লাইন
Hmm.
চার্ট দিয়ে তুমি যদি দেখাও তবে
Hmm.
সেটা অনেক বেটার হবে। তুমি এটা বার দিয়ে দেখাচ্ছ, এটা ঠিক হচ্ছে না। আমরা সাধারণত লাইন হিসাবে দেখাই, বুঝতে পেরেছো?
আচ্ছা ঠিক আছে, আমি যখন
তা তুমি
স্টাডি ম্যাটেরিয়ালটা
আরে
পাঠাবো।
সুন্দর বেরোয়, আরেও সুন্দর বেরোয় ওটা।
আচ্ছা আচ্ছা,
হ্যাঁ,
আমি স্টাডি ম্যাটেরিয়ালটায় লাইন চার্টটা ইনক্লুড করে দেবো, ঠিক আছে।
হ্যাঁ, ওটা দেখে নিতে পারো।
হ্যাঁ,
হ্যাঁ,
জাস্ট
হ্যাঁ।
এখানে স্টেপটা দেখানোর জন্য আমি এইটা বারটা দিয়েছিলাম, যাই হোক আমি ওটা ইনক্লুড করে দেবো ওর মধ্যে।
হুম।
So this is scree plot, just a visualization to see which factor to be included and which not to be. And this is again the same thing, that the total variances, the interpretation of the scree plot, I have told it in words, and these are written so that you can understand and write in exam. So the parallel analysis plot, Kaiser rule I have already told you. When the eigenvalue is greater than 1, we have to consider. Then the parallel, when we use the parallel analysis, simulate B that is greater equal to 1000 random correlation matrices, was that n and p must be same. Okay, compute the eigenvalues for each of those, take the 95 percentile at each of the factors position, plot real and random eigenvalues, yes, this one, real values and the random values, and we will be showing the differences. Okay, if f1, this part you can see 2.89, that is greater than 1.38, right? You can see this part, this, the crossover, this red will represent the like random part, and this blue will be represent the real. So real far above than random. For f2, still it is far above than random. F3, still it is far above. So these are the three factors we can be included. But after 4, you can see 4 to 9, these are less than real, are below the randoms, so we cannot include those. Okay, this is a heat map. Heat map is like just a coloring. I have explained this in correlation matrix, I have just changed the coloring. This is a visualization heat map, nothing else, nothing to be explained here. And yes, these are like kind of summarization, all of this, like what are the latent factors, observed variables, and how to deal with the elbow pattern, how to deal with the arrow pattern. Okay, so I am not going through this, these are exactly same, you just have a look. So yes, this is a path diagram, I would say, that 3 factors, 9 models, 9 item models. Here you can see this, right? For each of the factors we have 9, so for each of the factors we have 3 sub factors, like 3 variables, so 9 variables are there, 9 items are there. So this is a like path diagram. Okay, I have explained it in this portion and previous slides also. This is just a visualization of it. So that is it. Anyone have any question?
No, I have no idea about the parallel analysis. So this is very interesting that I have learned from you.
Okay, like uh, yes, like when we deal with the random eigenvalues and the exact item eigenvalues, that is the real eigenvalues. We will plot the real eigenvalues and the random eigenvalues also,
Uh,
and we will be doing some. We can put a line or a bar, okay, to see the differences. If the real eigenvalues are greater than the random eigenvalues, then the factors will be selected. These will be under our consideration. If those are like, it is some kind of like the scree plot, and these are some kind of similar, but not the exactly similar, because we are dealing with the random eigenvalues and the real eigenvalues separately. Okay, so this is the difference.
Okay, thank you, Sneha. I hope I can work on this parallel analysis later on because we have the data, so we can do that analysis
Yes.
and how we can generate the random eigenvalues and what will be the criteria that I have to know. But this is a very good approach.
Okay.
So, students, you have understood the importance of factor analysis because in social science research, usually we are dealing with several variables, and the variables, they are sometimes related with each other, and this relation sometimes creates the redundancy. Okay, so that is called the redundancy error. What Sneha has told you, the multicollinearity. If the multicollinearity is high, that means there is some redundancy. So same variable you are measuring with some other name. Okay. So this is a very serious issue. And you have understood different type of rotation. That is the Varimax rotation. Another one is the oblique rotation. So usually we follow the Varimax and oblique. In psychological research, educational research, we are giving importance on this thing. And this confirmatory factor analysis that Sneha has told you, this is vital because this is the assumed. So initially you have to do the exploratory type of factor analysis. After that, you can go for the confirmatory factor analysis. Sometimes I find in the thesis, that is the students, they have done the CFA and after that EFA. That is not justified. Okay. Okay, I think Sneha, they will study the YouTube video and they will learn.
Okay, sir. I will be providing the study material also. If they have
Okay.
any question,
Uh,
then I am like available to answer, obviously. So yes.
okay. Sneha, if possible, please you join tomorrow's program. huh?
Okay,
That is
sure,
the
sir.
Viksit Bharat.
Okay.
Now people are very much anxious. So I am inviting the senior professors. What is the Viksit Bharat and what is the architecture of Viksit Bharat? We have to
Okay.
understand